Okay, in this video I'm going to talk about the stiffness degrading oscillator SD and the effect of it on the maximum response. So the first thing that we want to highlight here is giving a kind of benchmark ratios of the maximum displacement demand as it has been calculated before by dividing the maximum displacement for the stiffness degrading oscillator means that single degree freedom system model, by that for the EPP. Of course, this is stiffness degraded or stiffness degradation oscillator or single degree freedom system, and this is elastic perfectly plastic model, as we have explained them in the previous videos, when both were subjected to actual ground motions. The meaning here is we are going to put the definition here that, or this kind of explanation on this graph, and I'm going to show to you what does it mean and how much it is important for us. We are going to put a graph that is relating between the period of single degree freedom system and the vertical axis is the ratio. This ratio is between the maximum displacement. Take care about delta here. I'm talking about maximum displacement of single degree freedom system, and whenever we use the word demand, means that it is due to an earthquake. Demand means that due to an earthquake or a ground excitation. So we are going to, or in this study, we are going to obtain delta for a single degree freedom system from using stiffness degrading oscillator SD. Maximum response is going to be calculated using nonlinear time history analysis, and this nonlinear time history analysis is going to be conducted for multiple actual earthquakes. The number of these earthquakes is 80 ground motions. So we are going to represent the mean of 80 ground motions, okay, over the maximum response of a single degree freedom system using a hysteretic rule, or the hysteretic rule, which is EPP, elastic perfectly plastic. Okay, if you do not understand what is the meaning of SD and EPP, please refer to the previous videos. Okay, so this vertical axis is representing this ratio. Okay, as I mentioned before, whenever that we are referencing delta EPP as a benchmark for us, this is because it is widely accepted as a reference, and also it is easy to be implemented. Okay, as we said, it is very easy to implement the EPP model because it's almost rectangular or almost square. However, for delta SD, or for the SD hysteretic rule, it is a little bit difficult, and in the same time it is going to you need to represent it in the model in a right way so that you are sure that it would give us the right response under the ground excitation. For those who didn't see the previous lectures, I have mentioned about them before here. Yes, these are the four types that I have spoken about. This is the stiffness degrading system, and this is the EBB model. So this is the hysteretic model, and we are comparing now between the two. So we have like one single degree freedom system, and at this point, for example, we modeled the hysteretic rule to be similar to this, and we have another single degree freedom system, and we put the hysteretic model here at the bottom. For example, here is EPP, and we are like putting the same ground excitation for both of them. So we are exciting them with the same ground excitation. And then we have done this for 80 earthquake. And from this 80 earthquake, we obtain the mean value. So whenever that we are talking here, if we are talking here, okay, here in this case, we are going to talk about the response between the two, the response or the ratio between the two, the maximum response for the mean of the maximum response for a single degree of freedom system, and we are calculating it for 80 ground motions, and we are getting the mean for it, and we have this ratio. Okay, so this ratio is going to be in the vertical axis and the single degree freedom system period is going to be in the horizontal axis. Okay, so this is period in S. Okay, and then we are going to obtain the ratio between the two. If the two responses are going to be the same, the mean response using this hysteretic rule and using this hysteretic rule, the ratio between them 1, means that they are going to provide the same maximum response, the same maximum displacement demand. Okay, and this is important for us to put it as like this is the benchmark here, or this is like 1. But we want to be sure that this rule can be applied for different types of structures with different ductilities. So we have applied it for different or on different ductility or response modification factor, different ductile systems. We're starting from 1.5, very low ductile system, to 6, for example, like high ductile systems, to see what are the responses of different systems on this ratio. And here we have given this graph for class D, or at least FEMA 440. It is giving it for site class D, and for other types of classes already there are similar graphs to this one. So this is only considered to be an example. Okay, and whatever conclusion that we are going to obtain here, it is considered to be also applicable to other different types of soil. So this graph is providing for us like a specific soil type. This is number 1. So the diversity of soil classes, as we said, it is already, they have done it for class B and C and D and so on. And number 2, there is diversity in the system that we are experimenting or that we are investigating. We have different ductility response modification factor. And number 3, there is diversity in the ground motion itself. We have used 80 ground motion. So this is considered to be like a good study or a suitable study because it covers different varieties of the system, ground motion, and in the same time the soil underneath. Okay, so from here I'd like to go to this title of this like group of videos. This is the title here. I call it degrading system response, degrading response, system response. Okay, and this is actually from FEMA, exactly from FEMA section 3.43, FEMA 440. So the word degrading here, I think that you have understood now what is the meaning of degrading, because we are going to use the maximum response coming from the stiffness degraded system, and we are going to obtain the ratio or compare it with the maximum response of a single degree freedom system coming from the reference model or hysteretic rule, which is EPP. Okay, so this is the meaning of the word degrading. And after that, for system here means that single degree of freedom system. We're talking about oscillator. Sometimes we call it oscillator, sometimes we call it single degree of freedom system. Okay, and this is response because we are talking about the displacement response of the system under the ground excitation. So it is the response. Okay, so this is the title of what we are explaining in this video, and maybe for the next video as well. Okay, here in this video I'm going to talk about delta SD. Okay, response. I'm not talking about energy here. I'm talking about the response, the maximum response. Okay, and we are averaging it over different number of ground motions. Okay, so this ratio, we are going to give it just a title here, or anything like kind of coefficient something. we can call it like C2. This C2, if you know about the displacement coefficient method, you are going to find that it is a coefficient that is being used by FEMA 356 in order to obtain this ratio. Okay, so let's go to the next slide, and I'm going to go back to the first slide. So actually the coefficient C2, which is in the vertical axis, it is the same like here. Okay, so this is C2 actually. Okay, the coefficient C2 is a modification factor to represent the effect of pinched hysteretic shape, stiffness degradation, and strength deterioration on the maximum, take care of this, maximum displacement response according to FEMA 356. Okay, even that FEMA 356, it is considered, this release actually considered to be a bit old, but it is important because it's a study. It is a solid fact that we need to take into consideration. And we can think about how FEMA even thinking about this and putting their coefficients. So C2 is going to be representing this ratio, and the horizontal is going to be the period of the structure, and we are going to, or at least show it for site class B. We have different site classes, okay? For a specific framing type, we have different framing type. You can find like bunch of graphs in FEMA 356 regarding this, but we are taking only one sample for it. And we are putting it with different levels, different limit states as usual. We have immediate occupancy, life safety, and collapse prevention, like 3 different levels of earthquakes. Commonly, these limit states, they are mapped into return periods of earthquakes. For example, immediate occupancy, commonly it is mapped with 75 return period. We call it return period of earthquakes. Okay, and life safety, it is the design earthquakes, like 475 years return period. And collapse prevention, it is like 2475 years return period. This means that the earthquake intensity is increasing with the increase of the return period. Okay, and we have like 3 different lines here. They are corresponding to 3 different levels of earthquakes. Okay, so you are going to find graphs for different site classes. You are going to find graphs for different framing type, and in the same graph, different levels of earthquakes, or at least different limit states, are being plotted. Okay, so the values of C2 for implementation in FEMA 356 depend on the type of structural framing system and structural performance, as we said before, levels being considered, like immediate occupancy, life safety, collapse prevention. Okay, this is only for C2. Which is the coefficient that is giving us the ratio between delta SD and delta EBB. So now let's go back to our main slide here. As you can see here, all the means of all systems for this site class, we are going to find that they are almost at 0.6. They are like going around 1, or maybe they are a little bit less than 1 in some certain cases, starting from here, for example, like 1.7 or 1.8 seconds. We're going to find a little bit less value, or the ratio is less than 1. Okay, so here, as we said, every line means that the mean of 80 ground motions. So the mean ratios were calculated for the different site classes. An example, okay, for ground motions recorded on site class D, this is only an example, as I said, is shown in this figure. Okay, with exception of periods of vibration smaller than 0.6 seconds, this is this part, he means, the maximum displacement of SD, the stiffness degradation models, are on average slightly smaller, from 3% to 12% than that of the EPP system. And this is right. Look here, if we say before and after 0.6. After 0.6, you're going to find the mean values. If we take the mean of these, it is going to provide us lists the maximum response of these systems modeled with stiffness degradation systems or models or oscillators are going to provide less maximum response than those for the case of elastic perfectly plastic models. Okay, this is, as I said, this is maybe counterintuitive, something that we surprising for us, because commonly whenever there is a system with EPP and another one with like pinched stuff here, okay, you are going to find that the energy dissipated here is less than here. So we are expecting the response of this system, the response of this single degree freedom system, to be larger than the response of this, right? Because the energy dissipated within the system, within the hysteretic rule, is going to, if it's large, this will reduce the maximum response. And the opposite applies, right? But here it is very surprising for us that almost they are the same, or even it is a little bit less. Okay, this is for delta SD over delta EPP. Okay, and the second part here, the second part is related to, let's go here. Okay, although this may seem surprising considering the smaller hysteresis loops of the SD model, as I have explained shortly, the results shown in this figure are consistent with previous investigation. All of these previous studies, they are giving the same results, or they are confirming that this kind of understanding for the ratio, or the ratio between delta SD and delta EPB after 0.6, it is going to be almost the same, or maybe it is going to be a little bit less. Can find, this is for famous people. I can read here like this: Clough, Chopra, okay, Fauch, Kronkler. Okay, so they are like very famous researchers. They are considering this as a fact now. Okay, so what is the point here? What we can conclude from this part? Okay, the point is, if we are going to have two systems, one is having stiffness degradation, let's assume it is something like this, for example. This is EPP system for a single degree of freedom system, okay? And this, I mean, this is model, the model, hysteretic model, and the other one is stiffness degrading model for, and we are going to apply it to the same single degree freedom system. The response coming from here, we can generally say that the response coming from here, which I'm going to call it delta EPP, is almost on average, it is going to be delta SD. Okay, what is the importance of this? It is a great importance actually, because you can, if you are interested in delta maximum of the system, which is the most commonly case for us, then you can just use this hysteretic rule, which is the elastic perfectly plastic, and then you can obtain delta EPP, which is actually, this model is easy to be implemented, and then we can obtain the maximum response. And the maximum response in average, on average, I'm talking about average here, is going to be on average equal to that maximum response going to be obtained from a single degree freedom system modeled with stiffness degradation hysteretic rules. Okay, and this is what the FEMA is taking into consideration by putting C2 in the displacement coefficient method, to take into consideration the pinched or stiffness degradation or strength deterioration of the model. Okay, so this is actually what I want to highlight regarding this video, and I hope that this would help us in modeling our single degree freedom system, and also understanding the point regarding FEMA 356. And using C2, you are going to find C2 for many cases equals to 1. So we can understand now what is the meaning and what is the rationale and background of using C2 equal to 1. Again, I'm explaining this, and I'm like putting an emphasis on this for longer period than 0.6, it is almost 1, but for period less than 0.6, you're going to find the ratio is very high. As you can see here, it is very high, coming to 1.6, sometimes 1.8. This means that the response coming from the maximum response coming from stiffness degrading systems is going to be much larger than that if we use delta E pp. Okay, so for 0.6 systems that is less than 0.6, which means that very stiff systems, okay, it is not right to use the delta or the elastic perfectly plastic rule. But for systems that is larger than 0.6, that is falling into what we call it the equal displacement rule region, it is preferred, or at least it is okay on average, to use the elastic perfectly plastic model. Thank you, and see you in the next video, which I'm going to explain about the SSD in this case, which is the delta of the strength and stiffness degrading system. Thank you, and see you in the next video.